Okay, in this video we're going to look at how to make a shear and moment diagram for a simply supported beam with a concentrated load on it. So in this example we have here support A, we have support B, and we have a 24 kip concentrated load applied 10 feet from the left support. We've already been given the reaction forces, so we don't have to calculate them. But if we needed to, we could, by summing the moments about point A in order to find reaction at B, and then summing the forces in the vertical direction to find the reaction at A. But since they're given to us, this is the procedure. Once all the forces are known, the best way to do this is to actually draw the shear diagram directly below the beam diagram. And start with a horizontal line. And this is going to represent a baseline of 0 shear. So this is the shear diagram. This value is 0. The way I like to think of this, the analogy I tend to use, is traveling along the beam from left to right, as though we're traveling down the road. And thinking of the loads that we encounter as increases or decreases in whatever you want to think of. I sometimes use the analogy of money. So we start off at the start of our journey, at the left end of the beam, and we encounter positive 8. So we go up a value of positive 8 kips, up to a value along this axis of 8. You can think of this as we start off a journey with $8 in our pocket. And then we travel along the length of the beam. So as we go along for the first 10 feet, nothing happens. There are no loads here in this part of the beam. It's just a beam until we hit this point where we hit 24 kips downward. So we started with 8, a value of 8 kips, and we then have to go down 24. And again, we can think of this as if we have to pay a toll to continue along the road. If we start with $8 and we have to pay 24, what does that leave us with? So that takes us all the way down to a value of negative 16. And then the remaining 5 feet of our journey, we don't encounter anything else. There are no more loads here. So you could think of this negative 16 as being in debt, $16, and then we reach the end of our journey, and what do we encounter but a positive 16? That's great. That takes us back up to a value of 0. So we have just created a shear diagram. Here's how to read this diagram. We have this block above this 0 axis, and we have this rectangular shape below it. If at any point I were to cut through the beam between support A and the applied load of 24 kips, and using a free body diagram determine the shear value, I would find that that shear value is 8. It's 8 all along that length of the beam. The point load of 24 causes it to drop way down to negative 16. So anything in between the point load and the right support, if I were to cut through the beam anywhere in that area and find the shear using a free body diagram, I would find that the shear is negative 16. So there are only 2 possible shear values here, positive 8 or negative 16. So depending on which point along the beam I check, I'm going to encounter a shear force within the beam of either 8 or negative 16. In this 10-foot length, it's positive 8. Over here in this 5-foot length, it's negative 16. Now the shear diagram is going to help us to create the moment diagram. And again, we should draw the diagram directly below the previous one. And again, we're going to start with a horizontal axis that represents a value of 0. There is 0 moment at either end of this beam because it's simply supported. I know the support conditions aren't shown here, but assume that it's a pin and roller connection that does not resist moment. If it can't resist moment, then there cannot be any moment. Otherwise, it would not be in equilibrium. So, we're starting at a value of 0. We can use the shear diagram to determine the value of the moment diagram. So what we want to do is we want to investigate any point where we have a concentrated load, or any point where the shear diagram crosses the 0 axis. In this example, those two things happen to be the same. At this point, 10 feet over from the left. So at that point, the moment is going to be equal to the area of this rectangle. So if we look at the area of that rectangle, the moment value can be found by taking the height of 8 multiplied by a width of 10. 8 times 10 is 80. So that means that if we come down here on our moment diagram, at this point 10 feet from the left edge, the moment is going to be equal to 80 kip feet. Now, how did it get there from 0 to 80? Well, the relationship between the shear diagram and the moment diagram is that the value of the shear diagram equals the slope of the moment diagram. So in other words, during this first 10 feet of the beam, the shear value was 8, meaning that the moment diagram is going to have a slope. It's going to go up 8 kip feet for every 1 foot traveled along that beam. And it's going to be a constant slope, which means the moment diagram is going to be a straight line, straight shot from 0 straight up to 80. Now, the slope of the moment diagram in the last 5 feet is equal to the value of the shear diagram. The value of the shear diagram is negative 16, meaning that for every 1 foot you go across, we're going to go down 16 kip feet. Okay, so if we start here with 80 and we're losing 16 kip feet for every foot traveled, and we travel 5 feet, 5 times 16 is 80. So we're going down from 80 down to 0. And so we begin and end at 0. And so these two diagrams combine to tell us what's happening in this beam as we travel along it. During the first 10 feet, the shear is remaining constant at a positive 8 kip value, and the moment is slowly increasing at a steady rate from 0, and it just keeps getting bigger and bigger and bigger and bigger until it hits a maximum value of 80 at the point of application of that point load. And then, in the last 5 feet, the moment value is going to decrease at a steady rate until it gets down to 0. And the shear, on the other hand, is remaining at a constant negative 16 kips. I should label my units here. These are all in kips, kips, kips. So the units for shear are units of force, kips, pounds, newtons. The units of moment are force times distance, so kip feet, or pound inches, or newton meters. So this is a relatively simple example. We only have one single point load, and these are what the diagrams look like. The shear diagram is has a horizontal line and then a big jump down at the point load, and then another horizontal line and a big jump back up. The moment diagram is shaped like a triangle with a steady increase in slope and then a steady slope down until it gets back to 0. Okay, let's see. I think I will stop there and end this video, and we'll look at the next example for what a shear and moment diagram look like when you have a distributed load in the next video.